So force is an external effort in the form of a push or pull which produces or tries to produce motion in body at rest. So motion in a body at rest. And second is it produces or tries to, uh, it stops or tries to stop a moving body. And the third, what it does, it can change or tries to change the direction of motion of the body. Okay, so it is an external effort which is in the form of push or pull, which produces or tries to produce motion in a body at rest. It stops or tries to stop a moving body and bring it to rest, and it changes or tries to change the direction of motion of the body. So how it does is, suppose there's a football on the ground and it is at rest. You want to bring it into motion, you have to apply a force, give it a kick, and the football will start rolling. So it is actually able to produce motion in this football at rest. Now if you place, instead of the football, there's a roller or there's a large stone, heavy stone on the ground, and it is at rest. You want to bring motion into this body, you apply a force, you kick it, but this large stone, because of its very high large amount of mass, will not move. So the motion has not been produced, but the force has tried to produce motion. So whether the motion has been produced or not, the force is existent, the force is there, it has been applied on the object, though it may not have been able to produce motion. So it is trying to produce motion. So then also this is force. We consider this is a force. Now suppose there's a body already moving and you want to bring it to rest. What you do is you apply a force in the opposite direction of motion and the body will come at rest if it can, if the force is good enough for that body, for that kind of motion. Now suppose the body is a large truck or a car and it is moving and you want to bring it to rest and you apply a force in the opposite direction. The force may not be able to bring it to rest, so it keeps on moving, but the force has tried to bring it to rest. So again, it may be, because in this case it is a push, so you're pushing in the opposite direction to bring it to rest. Though you may be able to bring it to rest, you may not be able to bring it to rest, but the force has been applied. And now third is a change or changes or tries to change the direction of motion of the body. Suppose a car is moving on the straight road, okay, and you want to turn it. What you'll have to do is you have to apply a force on the steering wheel and you have to turn the steering wheel. So you have to apply a force. Only that force can be able to make it go through a turn. So that force may be good enough. Mute yourselves, everyone. All right, so the force may be good enough to produce a change in the direction of that body, but force may not be good enough to change the direction. And then also we say that force has been applied, but it has not been able to change the direction of body. So this means that external agencies of force can produce change in the direction or try to produce change in direction can bring the motion to rest or can bring the body to motion from rest. Now the force in all these cases that we have discussed is a contact force. That means we have come in contact with the object in question. So we have pushed the object, we have come into the question when it was at rest, and we have stopped the object from its motion, and to bring it to rest we have come in contact with it, the force has come in contact with the object, and so on. So the force or external agency can be either a contact force or it may not be a contact force. So contact force or it may not be a contact force, a non-contact force. So the example of non-contact force are gravitational force or magnetic force. Because moon is being pulled towards the earth with the gravitational force. Also magnetic force. So magnets are able to pull the iron pieces toward itself without coming in contact with those iron pieces. So the force can be either contact force or it can be non-contact force. Aristotle's fallacy. So Aristotle was a Greek thinker, and he was there around the time 380 say 2 BC to 322 BC. So this much period he was present, and he studied objects in motion. So he said that the external force is required to keep the body in uniform motion. According to him, an external force is required to keep the body in uniform motion. That is, the body is covering equal distances in equal intervals of time. So this is what it appears, but it is not true. Suppose a body, according to him, a body has to be keeping on rolling on the ground with uniform motion. You have to apply a constant force. You have to keep on applying force, because otherwise the body will come to rest. But he could not uh, imagine that there is a opposing force, which is a contact force, which is called the force of friction. So friction can be friction due to the contact with the ground, or there is an air friction also. So all these opposing forces are all the time acting on the bodies. So when a force is applied, these counter these applied force. So that is why the body comes to rest after moving a certain distance. So that is why he said that to keep the body in motion, you have to constantly keep on applying the force. So when you are applying the force constantly, that means you are applying a force to counter the air friction as well as the ground friction. So actually, if there was no air friction, no friction due to the contact with the ground of the body, ground with the body, then we would not have to apply a constant force for uniform motion. So that was where Aristotle was wrong. So if there is no frictional force, then we would not need any force to keep a body in uniform motion along a straight line. Now Galileo's law of inertia. So all these you have already been introduced to all these topics. Now Galileo also studied the motion of the objects, and he used inclined planes to study the motion. So according to him, objects moving down a smooth incline accelerate. So when object is moving down a smooth incline like this, is moving down, it will accelerate. That means its motion, its velocity will keep on increasing with time. And second is objects moving up a smooth inclined plane. So now the objects are moving up. When they are moving up, what happens? They retard, the motion retards or deaccelerate. Okay. And the third point that is very important is that objects moving on a frictionless horizontal plane, on a frictionless horizontal plane. So if the objects are moving on a horizontal plane which is frictionless, then they move with a constant velocity. So objects move with constant velocity. They neither accelerate nor retard. Okay. So that is what Galileo concluded after studying the motion of objects on inclined planes. So he studied particularly by experimenting. Let us discuss three of his experiments. So he took an inclined plane. The inclination of the two planes was same, of equal inclination. And from a certain height, he released an object or a ball. So it keeps on moving, then goes to the horizontal and then goes up to the same height. So he observed that the height up to which on the other inclined plane the object reached was same or equal to the height from which it was released. Suppose it was released from a height h, it went up to the height h if there was no resistance due to air or contact with the surface of the incline. So if frictional force is not considered, or if the frictional force is not present, the object will go up to the same height on the opposite incline, which is at the same inclination. But practically we know that there is a frictional force present in nature, and therefore in practically the object will not reach that height. It will be lower than the height from which it was released. So h dash will be less than h because of the frictional force. But if we say that in ideal case there is no frictional force, it would certainly go up to the same height. So this is one example. Another experiment that he conducted was he took once again two inclined planes, and one of the plane had a slope which was smaller than the other. So slope decreased. So this is one incline, another one is this is horizontal, and this slope has increased. So certain height h, the body is released from this height. It keeps on rolls onto the horizontal surface, then goes up to the incline on the other side, and you see that the object reaches up to the same height from which it was released. You will see that the object will go up to the same height on the other incline, though there is a difference in inclination. So slope here is decreased than the first case. So inclination has decreased. So practically we again know that it will not reach the same height, it will be smaller because of the force of friction. But in ideal case, if there was no friction, it will reach the same height, though it will travel a larger distance in the second case. तो इस incline में स्मॉलर डिस्टेंस ट्रेवल करता है क्योंकि इंक्लाइन उसकी ज़्यादा है सेम हाइट से नीचे आने में, लेकिन इस इंक्लाइन में सेम हाइट तक पहुंचने के लिए उसको लार्ज डिस्टेंस ट्रेवल करना पड़ता है और फिर भी वो ट्रेवल करता है। यहाँ यह देखने वाली बात है कि वो उसको सेम हाइट तक पहुंचने के लिए लार्ज डिस्टेंस ट्रेवल करना पड़ता है और वो करता है। ठीक है, इस केस में डिस्टेंस जो है सेम हाइट में पहुंचने के लिए उसको कम ट्रेवल करना पड़ा था क्योंकि वो हाइट जो है वो कम डिस्टेंस पे थी। यहाँ पे ये हाइट जो है वो ज्यादा डिस्टेंस पे है, इसलिए वो ज्यादा डिस्टेंस ट्रेवल करता है। नाउ व्हाट ही डिड वाज इट टुक two planes, one was inclined plane, other one was horizontal. So now he released the object from a certain height, the objects keep on rolling and he sees that on the horizontal surface the object keeps on rolling without stopping. If there is no friction, if the force resistance, resistive force or frictional force are absent, then the object keeps on moving with uniform speed along the straight line. So that was the observation by Galileo. So from all these experiments, the conclusion that he made was that the state of rest or state of motion with constant velocity are equivalent. In both cases, no net force is acting on the body. So you can see here that the body is rolling without any net force acting on the body. So even if the body is at rest, no net force is acting, it will remain at rest. Here the body is in uniform motion and no net force is acting on the body. So these two states are equivalent. So state of rest as well as state of uniform motion motion with constant velocity or uniform velocity are equivalent, and in both cases the force acting on the body is zero. The net force acting on the body is zero. So therefore he said that Aristotle was wrong where he said that a constant force has to be applied to keep the body moving with uniform velocity or uniform motion. So therefore, to maintain a body in uniform motion along a straight line, we have to apply a force only if there is a frictional force. But if external frictional force is absent, we don't have to apply any force. And practically, if we do apply force to keep the body in uniform motion, we are actually applying force to counter or to oppose the frictional force. Okay, so external force is only being applied if we are making the body roll on the ground with uniform speed and applying constant force. That means we are working or applying force against the force of friction. So external force is being applied only to oppose the or to counter or balance the force of friction. If this was not present, we don't have to apply this force. So that is what Galileo's came out with after experimenting with bodies on inclined planes. So what is the conclusion? If the external force is zero, the body at rest continues to be at rest, and a body in uniform motion continues to be in uniform motion along a straight line. So that is also called the Galileo's inner law of inertia. So what is Galileo's law of inertia? If net external force is zero, the body at rest will remain at rest, and the body in uniform motion will remain in uniform motion along a straight line. Now from this we can define inertia also. So what is inertia? So inertia is the inherent property of a body by virtue of which the body changes, cannot, the body cannot change by itself its state of rest or uniform motion along a straight line. Okay, so inherent property of a body by virtue of which the body cannot change by itself its state of rest or uniform motion along a straight line is called inertia. So it can be any body, one body, and all bodies. This is true for all bodies. And linear momentum. Okay, linear momentum of a body is the quantity of motion possessed by the body. It is the quantity of motion possessed by the body. And we can measure this. The linear momentum of a body is defined as the product. It is the product of the mass of body and its velocity. So quantitatively, we can measure, we can get the amount of linear momentum in body, which is given by the product of mass and the velocity of the body. So we can say linear momentum is equal to mass multiplied by velocity. Okay, so we represent mass with the letter M, velocity with V, and linear momentum with small p. And all, so P is equal to M into V. So that is the expression. So mathematically, the linear momentum is P is equal to M into V. Now this is a vector quantity. Okay. Velocity is a vector quantity, therefore linear momentum, which is a product of mass and velocity, is also a vector quantity, and its SI unit is kg meter per second, because m for kg, mass is measured in kg, velocity in meter per second, and CGS is gram centimeter per second. So these are the units of the linear momentum, and dimensional formula of linear momentum: mass m L1 t minus 1. So from here, mass L and time t minus 1. Okay, now let us see the relation between P and V when mass is constant. So let us discuss when mass is constant, what is the relation between P and V, and you'll see that P is directly proportional to V. And what kind of graph we'll get? Suppose we have V along x-axis and P along y-axis. We get a straight line, which indicates that P is directly proportional to V when mass is constant. So we know expression m into v. So m is constant. So p will be directly proportional to v. Let us understand now the relation between mass and the linear momentum. If v is constant now, then p will be directly proportional to m. So m along x-axis, along y-axis. So this is the relation we'll get. So now v is constant. Third case, if two bodies have equal masses, say m1 is equal to m2. Two bodies have equal masses and have rather unequal masses, but the momentum are equal. So two bodies have equal momentum, linear momentum, but the masses m1 and m2 are not equal. Masses are m1 and m2 and velocities are v1 and v2, but the linear momenta are equal. Then we can write down m1 v1 will be equal to m2 p2, because p1 is m1 v1, p2 is m2 v2. So therefore m1 upon m2 will be equal to v2 upon v1. So that means if m1 is more than m2, v2 will be more than v1 and vice versa. Okay, so graph between m and v when p is constant will be not be a straight line but a curve like this. So which is heavier body will have small velocity and a lighter body will have large velocity. So it will be a hyperbola. Okay, now we can consider an example of effect of force and how linear momentum is important to understand the effect of force. So linear momentum can help us to understand the effect of force. Let us suppose we have to push a truck and a car and bring it to same speed in same time. Then we will have to use larger force to push the truck than the force required to push the car. तो अगर दो एक ट्रक में और एक कार में को हमें फोर्स लगानी है और दोनों को सेम स्पीड पे लेके आना है, v1 is equal to v2, ये v2 का स्पीड है इसका v1 का स्पीड है. तो if you want to make both equal, then we have to make force, apply a force which is larger in case of truck and smaller in case of the car. So F1 will be large and F2 will be small. So to make a large change in the linear momentum, a larger force is required. And because the mass of the truck is more than the mass of the car, so if mass is more, then to bring that to motion, a larger force will have to be applied. So effect of force, we can measure the effect of force if we know the mass of the body that we are trying to move. Now speed is another important parameter, and why it is, the example is a bullet is fired from a gun, can easily go through any human or any target before it stops. So that can be very injurious if it is coming from the gun. It is being fired from the gun. But if the same bullet of same mass is thrown at any person or any object, it will not be able to injure it that much. So what is the difference? The difference is in the velocities of the or the speeds of the two objects in two cases. In the first case, speed is very large. In the second case, speed is small. So effect of small speed is less. The effect of small speed is less. And the effect of the bullet with the large speed is more than the other one. So speed is another criteria that we need to understand to understand the effect of force. So if you want to stop a body with large speed, with high speed, you have to apply a larger force in comparison with the body. If you want to stop the body with slow speed, you have to apply a smaller force.